All right, so deals with rates of change, which we were talking about with the derivative, right? And we had two different types of rates of change. Anybody remember what they were? So like the algebra 1 way of a rate of change would be what? Like, if you're measuring a line, what do you need to figure out from that line? Slope, right? And we used that kind of, you had to use 2 points, right? So that was the average rate of change. And then once you got to calculus, you figured out that you only actually need 1 point to find the slope, and we call that the what? So derivative. What else? Like it's the slope at like that one particular instant. So that's say again. Right. So it's the instantaneous rate of change. Right, so you're going to have to kind of be asked to kind of compare the two. Right, you can come up with a rate of change in either using the average rate of change where you have 2 points and you're figuring out the kind of the slope between those 2 points, or the instantaneous, which is where you're finding the derivative. Now a lot of it is kind of this particle motion stuff. There's also a lot of physics based. So if you guys are taking physics, you might see kind of some parallels between the two. We're going to be talking about position, velocity, acceleration. When we are doing particle motion, we're just talking about a particle that is moving either left or right or up or down. So they're not moving like you have like a curve of a graph, something like that. The particle is not moving on that curve, but it's just moving to the left or to the right. So depending on what type of function you have, that's telling you how much it's moving to the right or to the left or up or down, depending on the position and also the velocity at a particular moment. All right, so a function can describe really anything, and then the derivative describes its instantaneous rate of change. So f of x could possibly represent area, temperature, rainfall, really anything that can be kind of quantified. So the derivative gives us a way to talk about how fast or slow something is changing at a single moment. Right? So at like 5 seconds, how is this, what's happening with the rainfall outside? So you're asking one particular moment in time. So one of the things you have to be kind of being able to do is being able to take mathematical sentences and then put it into words or English sentences. All right, so the first one you have is the temperature in degrees Fahrenheit of a cold turkey placed into a hot oven is given by T equals F of T. T is the number of minutes since the turkey was put into the oven. So right off the bat, you need to kind of get into the habit of kind of drawing yourself a graph of what the situation is describing. Now, you don't actually have to draw like a curve, but it's really good to kind of draw an axis and label your axis, because that's going to help you kind of label the units that we're talking about. So it says that it is capital T is equal to F of T. So my T variable is going to be my horizontal axis, and then F of T is going to be my vertical axis. So what does it say that the lowercase t represents? Minutes, right? So we can label that as minutes. And then what does the capital T represent? Temperature, right? So that is, right, degrees Fahrenheit. Okay. So it asks, what is the meaning of the equation f of 20 is equal to 255? Right? So again, you have f of t is equal to the temperature. So what does the 20 represent inside the parentheses? Minutes, right? And then the 255 is temperature, right? So since we're talking about putting a turkey into an oven, this is saying that at 20 minutes, right, after, turkey's been in the oven for 20 minutes, the temperature of that turkey is going to be 255 degrees Fahrenheit. So you could say at T equals 20 minutes, the temperature of the turkey is 255 degrees Fahrenheit. All right, so you have to get good with kind of labeling things too. So don't just say at T equals 20, right? Because your reader is going to think that, you're not really know what you're talking about. And usually on free response questions, one of the points that you get is units. So literally, if you just label stuff, you get 1 point. All right. Now it says, what is the sign of f prime of t? So, right, you put a turkey into an oven. So we're talking about what's the rate of change of that temperature of the turkey. So as you put things into an oven, what typically happens to them after time passes? They heat up, right? So the temperature is going to increase, decrease, increase, right? So it's probably not going to go like that. Like it doesn't infinitely just keep increasing temperature. If you put the oven at 350, that turkey's going to kind of go up, and then it's kind of plateau eventually after, say 20 minutes, 40 minutes, something like that. So probably our graph looks more like something like this. So kind of eventually it kind of levels off. But again, we are increasing, right? Our slopes are increasing as time passes, right? The slopes here are increasing. Even though this does kind of level off, they're still positive, right? So the sign of f prime of t would be positive. So f prime of t is positive since temperature is increasing. All right, next one asks, what are the units of f prime of 20? So anytime you are taking the derivative with kind of an application problem, you need to relate the y-axis units with the x-axis units, right? So really the derivative is kind of like a division process. So you're going to take what you have over here on the y-axis and then divide it by what you have, your independent variable over here, which is your horizontal axis. So if I were to put units on for that, what would it be? So like what's the y-axis unit? Right? And then the x-axis or the horizontal axis would be what? Minutes, right? So you're going to put, anytime you have a problem like this, is you want to put the vertical axis units over horizontal axis units. So f prime of t would be degrees Fahrenheit per minute. All right, so that would be your answer for letter C. Yep. Yeah. All right, now the last one says f prime of 20 is equal to 2. All right, so again, what is the what's the 20 mean? Right, so you can say at t equals 20 minutes, now, it's giving us the derivative, right? So the derivative is the what rate of change? Right. So, and it says that it's 2. So So you need to kind of connect the units that we just figured out for the last part, connect it with this, right? So the derivative is also the instantaneous rate of change, right? And since that number is positive, how does that connect with, like, the temperature of the turkey? Like, what's going on? Increasing, right? So since it's positive, right, at that particular moment in time, temperature should be increasing, right, because it's positive. Now, if that said it was, say, -5, then it would be decreasing. So the sign depends if your rate is either increasing or decreasing. So you can say at t equals 20 minutes, the temperature of the turkey is increasing by 2 degrees Fahrenheit per minute. Right, so since it's positive, right, that's where the increasing part comes from, and then the degrees Fahrenheit per minute is the units of the derivative. So it's the rate of change of, again, the vertical axis over the horizontal axis. Instead of like per 5 minutes or 10 minutes. Good question. I mean, usually it's always like kind of by like your second unit is always like by 1. You don't have to kind of worry about, okay, it's going to increase 2 degrees for every 2 minutes passed. It's always going to be your unit down below is always going to be 1 on the bottom. Yes. So that means that that could be that. Yeah, it could be it's reached its highest temperature, or it could be at a point where, if your slope is increasing or is positive, that means that something is increasing, and then eventually, if it kind of levels off at 0, that means that it's going to start decreasing again. So your sign actually might start. So say the temperature of the turkey was like 300, and then after like 20 minutes, it's going to start maybe cooling off, right? Maybe you took it out of the oven, and that's why the slope, you got to go from increasing to decreasing. You have to hit 0, right? Okay. Any other questions on that one? Again, the more that you do this, the better that you're going to be able to recognize, what they're looking for. All right. So again, the units of the derivative will always be the y-axis units over the x-axis units, and again, remember that the derivative is a division process. One reason that we write Leibniz notation, right? df over dx, or dy over dx, all that stuff. That's what's called Leibniz notation. So you're taking the units again of the vertical axis and dividing it by the units of the x-axis. All right, so f of t is the amount of rain in inches fallen since midnight, where t is the time in hours since midnight. Interpret the following. Okay, so I have f of t. So what would the horizontal axis represent? Time in hours, right? So hours since midnight. And then the vertical axis would be what? Inches of rain, right? Okay, so what would the derivative be? What would the units of the derivative be? Inches per hour. Good. Right, so that's a good habit to kind of get in even before you start answering the question. If they are, clearly they didn't give us an equation, right? So they're just asking about the rate of change over a period of time. So get into the habit, again, of drawing your axis and then coming up with the units of your derivative, because they're going to ask you for it. Okay, so what does f of 10 equals 3.1 mean? So again, we have f of t is equal to inches. So what is this? What does 10 mean? 10 hours, right? So t equals 10 hours. Now, when did we start? When does it say we started paying attention to how much rain was falling? Midnight, right? So 10 hours after midnight would be, okay. So at 10 a.m., how much rain is falling? 3.1 inches of rain has fallen. So they're right. This is like your original position function. So they're asking more of a kind of a collective unit over a period of time, where right the derivative would be one moment at one particular time. All right. Now the next one says f to the negative 1 of 10 is equal to 16. So what does f of negative 1 mean? What are they asking you for? What's that notation? Inverse, the opposite. All right, so we should probably draw ourselves a axis for those. So this is your f. So again, we still have the t, and we still have f to the inverse of t, or inverse of f. Right? So whenever you have an inverse of something, all you literally do is they literally switch. So what is the label for the horizontal axis going to be now? Inches, right? And then the vertical would be hours. Right? So now if I were to take the derivative of the inverse, what would my unit be? Hours per inch, right? So if I have inverse of f at 10, it comes out to be 16. So what does that mean? Right. So by the time 10 inches of rain have fallen, 16 hours. Something along those lines. The only way I would write it more in this order is because you kind of want to do like your independent variable first and then your output like second. That would kind of be my only recommendation for that. Okay, so it says f prime of 8 is equal to 0.4. So again, the 8 represents, so now we're going back up to the first graph. So the 8 represents what? Right, so 8 hours would be at what time? So at 8 a.m. Right, so now we are talking about the rate of change of the rainfall. So what's happening? What is that 0.4 going to tell me? the amount of rain falling is increasing by 0.4 inches per hour. Right now, so you're kind of just going to switch it around. So what's the 5 represent here? Which is rain, right? So when 5 inches of rain have fallen, 2 is going to represent what? Hours, right? So that's talking about time, right? So as this is positive, that means that time, what is time doing? Good, right. Time's passing. At 2 hours per inch of rain. Right, so at this one particular moment, right, when there's 5 inches of rain, right, they're saying that you're getting a rainfall of 1 inch for every 2 hours passing. Right, so at that one particular moment when 5 inches have fallen. Right, so again, get into the habit of, drawing these axes. It's a lot easier to, in my mind, kind of get a visual of kind of what's going on. All right, so again, we talked about instantaneous, right? That's the derivative. So whenever you guys see, rate of change at some moment in time, we're usually talking about the derivative, instantaneous rate of change. So a lot of these next terms here is you really kind of need to be familiar with this entire box here. Is also talking about particle motion, right? So what we're going to do is we're going to let position, right? So where you're standing at a particular moment in time is usually the first function that you're given, okay? And then the velocity, right? So if you look at the first bullet I have there, the derivative of position is equal to the velocity. So the velocity at any moment in time, or the velocity of the position of a particle as it's moving, all you need to simply do is just find the first derivative, and that will give you velocity, right? So it's like, if they have an equation that's going to represent my position of, if I were to go for a run, right? And all right, he's been running for 20 minutes. What's his rate at 20 minutes? You'd have to find the first derivative, which would give you velocity, and then you would plug in 20. Okay, he's running at a rate of 5 miles per hour at 20 minutes. All right, displacement. If you guys have never heard of that word before, displacement is really simply just a change in position. All right, so you're going to take your one endpoint, your second endpoint, and you're going to subtract your first endpoint. Right, so change in position is, say if I'm starting right here, right, and then after a while I stopped here, you're going to take where you stopped, subtracting by where you started. And that'll give you, how far have you walked, or how far have you ran over a period of time. Right, and then distance traveled is kind of connecting with position. It's the sum of the absolute values of the distance between resting points. So if you have a graph that say kind of looks like this, right? And they want to do distance traveled. So say my position is here, right? And I walk over here, I walk back, then I walk some more. I might have only walked 5 steps from where I started, but my distance, even though I walk back and forth, is more than 5, right? So anytime you kind of like change direction, you still need to account for distance traveled. So this is saying, all right, this guy's walking to the right, and then once he gets to about here, now he's walking left, and then he ends up back where he started, right? So I could have walked back and forth and still ended up on that same square, but all the distance, you're still accumulating distance over a period of time, right? So you want to look for, again, resting points. So this is a resting point, that would be a resting point, right? When you kind of change your slope, kind of changes direction from either going positive to negative or negative to positive. Average change in position is called the average velocity, and you get the average velocity by using this kind of difference quotient setup. All right, so it's the change in position, which is what you get on the top, over the change in time, you might say. All right, so that's kind of your algebra 1 way of figuring out the slope of the line. Instantaneous change in position is instantaneous velocity. So again, if you just take the first derivative, that'll give you the velocity. Instantaneous change in velocity is called acceleration. So these are kind of like the big 3 that you need to remember. So you start off with position, you take its derivative, you get velocity. If you take velocity's derivative, you get acceleration. Okay? So velocity will give you the slope at any point of position, and acceleration will give you the slope of velocity. Right? So they're kind of all connected to each other that way. So you have velocity will give you the rate of change of your position, and then your acceleration will give you the rate of change of your velocity. Right? So they're all kind of connected with one another. Yes. So you start with position, right? If you take its first derivative, you're going to get velocity. So that's going to give you the rate of change of your position at any moment in time. And then the derivative of velocity is going to give you acceleration. All right, so those are like the big 3 that you kind of need to remember.